everybody. Today our speaker is Alexander Zuevsky from our institute, and he's also participant of our seminar and even founding member of the our seminar. Today he should give a talk on conformal field theory correlation determinant with elliptic functions. Please.
Thanks very much. So first of all, I'd like to thank organizers for the opportunity to give this seminar. So it's a joint work with Daniel Levin and my colleague from Korea. So today we are going to discuss some applications of computations of correlation functions, those applications of those computations to number theory and to some further theory of identities for elliptic functions. So I prepared this talk to be as simple as possible to be able to deliver some thoughts about this science. So first of all, let me give some introduction. The computation related to vertex algebras is a natural source to get identities in number theory, in particular, in the simplest case for elliptic functions. And those computations, if we do using some vertex operator algebra technique, lead to closed and precise expressions for such identities, and starting from computations of correlation functions for corresponding conformal field theory. So there are various ways how to compute correlations functions in CFT associated to a particular vertex algebra, and in general, for some basic examples like fermionic or vertex operator algebra, there is a procedure which is called Bosonization, and which provides an alternative expressions for correlation functions. And those two approaches we can use in order to derive quite interesting identities for elliptic functions, since correlation functions themselves can be expressed through elliptic function in the case of genus 1, for example. Among those identities, we can mention some generalizations of classical phase tricyclic identities coming from algebraic geometry, and also some identities for eta function, which is a classical object in number theory, and also in calculations associated to the algebras, according to Katz, for example. And for those, sometimes we can call them generalizations of triple Jacobi identities, and we'll see how actually it works in conformal field theory of the computations associated to vertex algebras. So the basic, the fundamental object that we start with is so-called genus 1 endpoint function, or twisted genus endpoint function, which is a trace or super trace of a number of vertex operators multiplied with some q parameter to the power of the grading operator L0, which is a L0 mode for the Virasor algebra. So altogether, when we compute a trace over a modular of our vertex operator algebra, we can find some meromorphic functions which can depend also on some twisting parameters or group elements, depending on their presentation f and g, which actually twist the whole product inside the trace. That doesn't work probably properly. So the product inside brackets of vertex operator and the other parameter g actually can deform or twist the modular over which we compute that partition function. So the parameters z's are here are defined on the torus, and these are elements of our vertex operator algebra. As I said, L0 is the Virasoro zero mode, which plays the role of the grading operator in our vertex algebra V, and C is the central charge as always. As I said, this is a basic object in computations of correlation functions at genus 1, which means on the torus for a particular vertex operator algebra. So there are two kinds of formulas and kinds of functions that we obtain using computing that trace, which can be associated either to some bosonic structures. In that case, the generating function for such traces can be expressed through Bergman kernels, or in the case of fermionic algebras, we can express them through so-called Giga kernels. Let me proceed with some. So in this talk, we will try to find some formulas related to genus 2, the computations of genus 2 partition and correlation functions for our vertex operator algebra in terms of geometric construction of solving two, for example, solving two tori, or a self-solving of a tori to get a genus 2 Riemann surface. So in that case, our formal parameter z, which we saw on the previous slide, will be related to local coordinates on the resulting Riemann surface that they obtain by solving two tori. And as a result of those computations, we can find some explicit formulas of powers of the modular discriminant, which is the 24th power of eta function, the classical eta power function. And those formulas turn to be useful in particularly in many areas, many sub-areas of number theory, and also it's important for computations of correlations functions at higher genuses for a vertex operator algebra. And finally, it can be used also to compute some cohomology stuff really associated to vertex algebra. So what we are trying to get is quite fundamental objects, some fundamental object. And it's interesting that in recent papers on number theory, they actually try to use numerical calculations in order to get some expressions for powers, for complex powers of eta function, and formulas that we get in the course of this talk actually provide us with explicit formulas in terms of some determinants, and that's why. And we will find that those determinants are play quite important role in this picture, and that's why actually the name of the title of the talk is related to determinants. So that determinant structure is quite important in computations of higher objects. So let me give some.
Very quickly remind the operator algebra. You extend the classical formula related to genus 1's elliptic curve to the higher genus, yeah? Or you say that the
let me explain. So in that case, I have to get back to this formula once again.
Maybe not what's the answer your first seminar, and you explain a very big algebra. So it's a not how to say, waste the time to remind even somebody like me, yeah? Check kind of.
Well, I'll briefly remind. No, not otherwise I wouldn't be able to get to the very end.
Yeah.
So vertex algebras are generalizations of Lie algebras, They are constructed in terms of vortex operators, actually those objects that we have here, which are expansions over some non-commutative modes of elements of our vortex operator algebra V and powers of corresponding formal parameters Z's. And those vortex operators satisfy natural commutativity, associativity, and Jacobi properties. The Jacobi property for those in specific situation for those vortex operators. So it's quite natural generalization of Lie algebras, and it turns out that this is the language of conformal field theory. Actually, the conformal field theory in particular case of vortex algebra is vortex algebra itself. So properties of vortex algebras describe in the best way the conformal field theory that we have for a specific case. How we characterize those vortex algebras in our sense? We compute functions like this. So in this, for elliptic case, when we consider elements of when we consider formal parameters sitting for vortex operators sitting on a torus, which means elliptic case, as a result of the traces, as a result of computations coming from conformal field theory, we obtain elliptic functions, which means double periodic meromorphic functions, as characterizing in numbers the actual properties of vortex algebra. That's when we want to construct some sort of a higher genus case, we can either start from the very definition of vortex operator algebra at higher genus, which is a different science in some sense, or we can use some geometric constructions, some constructions of higher genus Riemann surfaces, starting from solving, for example, this is just the one geometric, not exhausting the whole set of cases, and solving from torus to get a higher genus Riemann surface. So in order to construct corresponding functions describing vortex operator algebra at higher genus, we have to use these functions and to introduce a procedure how actually we manipulate with those functions in order to get some meromorphic function which would satisfy definition of a correlation functions for our conformal field theory. So of course that the whole series should be coherent inside itself, and it's a big problem to get all parts together and to prove the convergency of such objects. But more or less recently that theory become stable, and now we know how to do this at higher genus. So this is basically the description. So let me pass to the next and to more specific things. So as I said, the modular discriminant is written here. It's a 24th power of the classical eta function, which is defined by this product. It's a Q series, and it's interesting to find some explicit expressions for powers of delta. As I said, for many reasons, I will not even try to enumerate all cases where those powers, in which those powers become interesting, especially for the complex case when we have some complex powers. So in number theory, they sometimes expand those powers in order to get some number coefficients for corresponding power, taus, for example. But we'll see that it's we can avoid this by doing our calculations. So the other object, which is quite fundamental, is called the Eisenstein series, is given once again by by some specific Q series. It's written here with Bernoulli number. And these En functions are fundamental objects for computations of correlations functions in the bosonic case for vertex operator algebras. So, which means that all all correlation functions for a bosonic vertex operator algebra of rank 1 or 2 can be expressed in terms of some series of En functions. So En functions, as I said, is also classical objects in number theory. And what is important for us that Ramanujan found in his classical 130 pages work, found some relations for E functions. So basically, E8 is square of E4, E10 is the product of E4 and N6, and E12 is these combinations with some coefficients. Depending on a particular presentation of E, those coefficients could be different, so don't pay much attention for those coefficients. Which means that we have a basis in which all En functions can be expressed in some way as products of En functions. So we will use those formulas later on, in particular in this expression for the delta functions for our modular discriminant. So this is given by this. You can compute this by substituting the 24th power for theta. And Ramanujan found this formula as a determinant of E4, E6, and E8. And then Garman conjectured the formula for the square, where is it? For the square of delta function, which in turn can be expressed in E4, E8, E12, and in E10 and E8. So as a determinant. That formula was proved by Milne, and he also found several, something like 20 pages of formulas related to those determinants, but not in this clear form. Then there is only one determinant. Those determinants for different orders of delta were written in terms of some E function multiplying the determinants. So, which shows that the basis of E functions only doesn't really correspond to the clear and explicit form for powers of delta functions, only in terms of determinants. That's why we were trying to find some more explicit determinant which would not include the products of E functions to the determinants, but only some specific only for some specific matrices in terms of determinants only. I mean the powers of delta function. So it turns out that those formulas can be obtained from certain computations of genus 1 partition functions, which means that the expression where we don't have any vertex operator inside the trace. So there are two ways how to compute as I said, there are two ways how to compute a partition function for in the elliptic case for a fermionic vertex operator algebra. And one of those formulas is the direct computation through the fermionic structure. It's this formula actually in some simple form exists in Katz's book on vertex operator algebras, and with some further insertions of some further twisting parameters, twisting group elements F and G into the partition function, we can find it in terms of a product. And in the bosonic case, it can be also after the Booleanization procedure, we can find some formula in terms of theta functions and eta functions, which gives us a hint how we can use the comparison of these two expressions, with the same expression actually in terms of different objects, to get powers of eta. So let me remind you that theta function here is this sum of products, the classical theta functions with the parameters A and B. And on the next page, I'll show how actually beta, alpha, F, and G depend on each other. Sorry, it's the wrong way. So we have two group elements, F and G, which are exponentials of the Heisenberg element in our zero mode of the Heisenberg subalgebra in our rank 2 free fermionic vertex operator algebra. So these two elements twist if we get back to the original formula for the trace, one element twists the product of vertex operator, and the other element twists the representation of our vertex operator algebra, namely this curly V. These are two group elements. Alpha and beta are some real parameters parameterizing the group elements. And insertions of these two parameters. Also, we have some auxiliary parameters, theta and phi, which are exponentials of alpha and beta. And then we have actually two cases. One case is that both theta and phi are ones. And the other case when alpha, theta and phi are not both equal to 1. So in that case, we get, comparing these two formulas on the previous slide, actually these two formulas, we obtain an expression for eta function, which is the classical formula written in a different way and shows that the first power of the eta function is given by theta function, some exponential depending on parameters that we introduce in order to twist the trace, and the determinant. And this determinant is given by this. And it turns out that this determinant can be also interpreted as in geometrical way, in the sense that the exact computation, fermionic computation of the partition functions and genus 1 can be seen as a result of the self-solving a torus from getting torus from the sphere, actually, it's not written in the correct way. Getting torus from a sphere by self-solving when we solve it a sphere to itself. Then we get this expression, and the determinants of this matrix appears in the expression for the first power of eta function. So now we proceed to the higher genus. Sorry, not yet. What we want to get from those computations, we want to get some expression for other powers of delta functions of the, sorry, it's like this. Written in terms of elliptic functions and determinants of elliptic function. For that purpose, we have to introduce a different basis for our elliptic functions, basically the deformed elliptic functions. So let me start with these functions En, which has two parameters, theta and phi. In the definition, let me remind you that theta and phi are exponentials of alpha and beta, and they're related to the twisting group elements of our trace, and it now gets two separate summands in the formula. So it's a generalization of the classical Eisenstein series with some parameter theta and lambda inserted. And they also introduced so-called twisted or deformed Weierstrass functions in this line, which can be expressed in terms of twisted Eisenstein series. And at when theta and phi are both equal to 1, the P and E go back to the classical Eisenstein series and Weierstrass functions. Deformed, you saw on the previous slide that we had E functions. You see, it's given by this series.
Yes.
Now we want to introduce two parameters so that the properties of those functions, parametric deformation of those functions would have similar nice properties. So those parameters are introduced here in coherent way, and when we send theta and phi to both to 1, we can see that the P2, this P2, the classical Weierstrass function can be related through E, and there is a limit from those functions to the classical functions. Moreover, the original ENs are so-called quasi-modular forms because E2 doesn't satisfy in full the modular invariance, and deformed EN and PN, they satisfy the modular forms with respect to some groups. So, in order to express the Fermi structure, it's not enough to use only ENs without deformation. You have to add an extra term with some deformation in order to be able to express correlation functions at genus 1 for corresponding vertex algebras. So these are quite standard representations for our deformed elliptic functions, which satisfy quite nice properties, and these are bases which we use in order to express the genus 1 correlation functions in more suitable way. Let me also introduce some auxiliary capital theta, which is a product of theta functions, just to shorthand the notations. And finally, let me introduce also some matrices, the matrix of P1 functions. P1 we saw on the previous slide here. So P1 is upstairs, is expressed through the E functions. And also some Qn matrices corresponding to the case where theta and phi, in the first case, they are not equal to 1, 1, and in the second case, they are both equal to unity. So as a result, we have an expression for all z powers of delta function in terms of theta functions. So this block corresponds to some quite complicated combination of theta functions and the determinant. So you see, let me remind you that in Milne papers, those n functions were products of ordinary En to determinants of matrices containing classical En. Here we don't have any more extra products. We expressed everything in terms only determinants of deformed P functions. And in the case where our theta phi parameters are equal both to 1, then it's similar structure with a determinant with different theta functions and different metrics inside the determinant. So this is the explicit expression for all n powers of modular discriminant, which looks quite good, and we also can use them. The right-hand side can be expanded as a Q series, and you can insert any number as a Q and obtain any power of with respect to tau very easily. So it's not a problem anymore to estimate some dependence on of the delta to the power n in terms of powers of tau. See, so as I said, this is the explicit formula. Now, this is the genus 1 case, which means that all functions on the right-hand side are associated to those are elliptic or quasi-elliptic functions, and they can be used in order to compute correlation functions for our vertex operator algebra. This determinant actually plays the role of some sort of a generating function of all correlation functions in genus 1. And the question is how universal this formula, in the sense if we change the genus. Can we get the same formulas, for example, for powers of n in terms of higher genus functions on the right-hand side? Because you see, this left-hand side is a part of a partition function, so which means that we can, since in our construction all partition functions for higher genus can be expressed through the lower genus correlation functions, then the partition function of the resulting partition function higher genus would more or less remain the same up to some expression. You see, it's a constructed object, but what is interested is some relations to the right-hand side, which express in particular genus. So we probably fix the genus, fix the left-hand side, and start to find out if we have the same expressions it's at higher genus, which would give us even more complicated and interesting formulas for the left-hand side, you see. So first of all, at higher genus, we can also compute more complicated expression for delta n functions. So and for that purpose, we should use so-called prime form. That prime form is, I'll give the explicit formula later on, the definition, but we know that for a genus 1, it's given by this formula, the theta function to some specific twisting parameters and a third power of eta function, which is quite useful. And in computations of the genus 1 fermionic endpoint functions, we find the formula for the determinant of our Pn functions. Let me remind you that these are matrices of P1 functions for some n. It's a finite size matrix. And this determinant of such matrix can be expressed through the theta functions and product of prime forms. So if we insert this formula into this formula, and this formula is called the generalization of the classical phase trisecond identity. If we insert that formula to this formula, we obtain some expression which we saw on the previous slide, which means that we can express either in terms of theta functions, this formula, or in terms of purely in terms of prime forms according to the first formula. So no matter how we express some powers of theta would appear, and we can use them as a formulas for powers of theta functions, which is quite good. And the same case we have for when theta and phi is equal to 0. So formulas on the previous slide, basically those formulas for powers of delta appear from the formulas for phase trisecond identity in genus 1. So for more complicated expression, when we actually expand those P1 functions in terms of some the auxiliary basis of D functions in a specific way. So the expansion depends how we actually treat the expansion of Z1 and Z2 that we have in our P1 function. Then we can form a determinant of these M functions with D elements, D coefficients. And in that case, we obtain even more complicated formula for some phi given by Z number. And this would be the power of corresponding delta function. So the most complicated case of phase trisecond identity for the correlation function would give the formula for some combinations of N and M, and this is actually the same formula but written in different bases again. So if we want to use this basic for a specific number theory purposes in terms of D expressions here, because they are coefficients in this particular expression, when we start to express the powers of n eta functions, it might be useful to use this formula for some numerical properties. Let me pass finally to the genus 2 case. In that case, let me explain how we get the genus 2. As I said, the geometrically genus 2 case in our specific geometrical configuration can be obtained as either solving two tori or self-solving of one tori to get a genus 2 Riemann surface. So this is a quite standard and stable operation, how we actually express corresponding objects on a genus 2, there's some differential objects on the genus 2 Riemann surface starting from a similar object at genus 1. And similarly, we can express our correlation functions in terms of at genus 2. For example, the partition function when we don't have vertex operators. In terms of lower genus partition function and some determinants. So I promised to give a definition of the prime form. The prime form is defined like this. So this is the theta function divided by some half-order holomorphic forms on a torus, and these prime forms, the functional prime of the prime form can be used in order to compute the partition function. So the first formula for the specific values of the twisting parameter alpha and beta equal to 1 can be written in terms of prime form divided by the square of eta function. Again, for in the genus 2 case, we can use computations directly from the fermionic genus 1 in order to get the genus 2 partition function. So basically, it results in as a product of two genus 1 partition functions with two sets of deformation parameters. So f and g are vectors here of f1, f2, f and g1, g2, and multiplied by the determinant, which comes from the fermionic structure. And I'll show you what Q matrix is on the next slide. So this is square root of the determinant for in the fermionic case. And if we have to compute the same partition function in the bosonized version, we can once again find the we can use the expression for the partition function at genus 2 for our bosonized version of our vertex separator algebra, which also has some determinant structure here for matrices A1, A2. I'll show in the next slide with theta function, and depending on the period matrix of the specific Riemann surface that we obtained from the genus from solving of 2 tori. So Q matrix in that sense, you saw this Q matrix in the formula for the genus 2 partition function. So Q matrix is this matrix expressed through the blocks. In that case, you have infinite blocks for anti-diagonal infinite blocks of expressed through some twisted Eisenstein series with specific parameters. A here is 1 or 2 because we have, in that case, 2 tori. We have 2 sets of correlation functions for each tori, and A stands here for the choice of the left or the right tori to get a genus 2 Riemann surface. And A matrices, which we saw in the bosonized picture here, is given by genus 1 Eisenstein, ordinary Eisenstein functions. So with some specific deformation parameters, alpha 1/2. And if we compare the expression for these two genus 2 partition function, we obtain a formula expressing the product of the third power of the eta function, depending on 2 parameters, tau1 and tau2, which are modular parameter for our 2 tori, some prime forms, some powers of prime forms, and the determinants. So we see that the structure of powers of eta function continue to be some coefficient in terms of theta functions multiplied by some determinants or power of determinants. And in particular, if we take the similar tori, in some sense, we obtain the structure, once again, relating the 6th power of eta function in terms of determinant, the square root of determinants and determinant of the Q matrix. So this formula is, once again, a generalization of the classical Ramanujan formula for eta for the 2nd power of eta here, or a generalization of the Miller formula for the 3rd power at the determinant, but expressed in terms of deformed elliptic function. So unfortunately, Ramanujan didn't know about the deformation. He would write another 200 pages of formulas related, but it's just one formula. He had a very wide collection of bunches of formulas, I would say, like that. So you see, that's just an example how we actually use the deformed elliptic functions in order to produce more sensible expressions for powers of the classical object as, for example, eta function or the model discriminant. But that's not the end. Actually, first of all, first of all, we can use the same idea of, remember when we derived the genus one formulas for eta functions, we used phase transsecant identity. The same generalization for the phase transsecant identity exists also for the genus 2, and the same thing for the classical Jacobi triple identity. So in the computations of genus 2 partition functions, we can find this formula as a generalization of the classical triple Jacobi identity. You cannot see it probably the same structure as, let me show you the original formula in some initial version, this formula. So this is the triple Jacobi identity written in a different way. And in elliptic case, in genus 2 case, you have, instead of that simple formula, you have more complicated formula of this type. So it's convenient to write it as the ratio of genus 2 theta function and some combination of once again theta function depending functions. Here, this formula actually corresponds to the so-called self-sewing case of a torus in order to get genus 2 Riemann surface. So in this formula, we can see once again determinants of some auxiliary matrices, which would play this further role in our search for higher powers of the modular discriminant. And that parameter kappa has a geometrical sense, since it counts the, actually it describes the coverings of the original tori when we self-sew it, to itself in some way. So that parameter kappa is is limited in this region, and in the formula above, our matrix is given by the block structure of our expansions of the listed elliptic functions. So we see C1 here, that should be 1 here and 1 here. C1 is the coefficient, is related to the K plus L Eisenstein series, the classical Eisenstein series, and D is related to Weierstrass, the classical Weierstrass function at genus 1. And T function is this matrix with some theta parameters. D is a matrix. I'll show you on the next slide. So, so Q is a matrix. Pardon, and this is the wrong way. Once again, sorry. The D is a matrix of our twisting parameters multiplied by delta function, and G matrix is a matrix which contain expressions for Giger kernel, the the reproduction kernel for genus 2 correlation functions. It can be written explicitly in terms of, once again, twisted elliptic functions, and it can be written in genus 1 and in genus 2. So basically, the Giger kernel for genus 2 can be written in terms of these functions, which are genus 2 generalizations of the deformed elliptic Eisenstein series. In some different representation, you can find explicit expressions for E2, for the genus 2 Eisenstein series, which hints us that there should be some determinantal formulas for delta function, for powers of delta function, for the modular discriminant. And as I said, the original formula for the triple Jacobi identity actually allows us to produce some further formulas for delta function. So for that purpose, we introduce some extra, it's on the next line, extra semi-infinite matrices H and H bar to simplify our notations. They contain those expressions through the Giga kernel. And so all those matrices are prepared in such way so that the final expression would be as much simple as possible. This Giga kernel with sub index kappa is actually part of the genus, the full genus 2 Giga kernel, full genus 2 reproduction kernel, which can be expressed through the, once again, theta functions, or this. And starting from the classical Jacobi, from the generalization of the classical triple Jacobi identity, we can write a formula which express the, once again, some power of non-integer power of eta function in that case, in terms of, once again, as we saw in the classical genus 1 case, the product of theta functions. This, in this case, these are genus 2 theta functions depending on genus 2 period matrix for our Riemann surface, and multiplied by determinants, the ratio of determinants of Giga kernel. You see, it should be bracket like this. It doesn't fit the size of the screen, unfortunately. And we see that in that case, we obtain a formula for some power of eta function on the left. And similarly, we can find the corresponding formula for the modular discriminant in terms of a combination of theta functions and determinants of matrices containing genus 2 generalization of Eisenstein series. As I explained before, the left part of this formula is not very important because these are some specific examples. What is important for us that the general structure of all powers of eta function in some way can be written in terms of that theta part, theta functions multiplied by determinants. And this conjecture, how to say, unifies all the cases which we had in genus 1 for various representations, and hints us that at higher genuses we have the same formulas, actually, same how to say, same form of formulas. So as we conjecture, should be more or less at the same form. So this specific case is explicit formula for all values of kappa in between -1/2 and 1/2, and it also depends on this matrices of Giga kernels. Again, this is what is important for further discussions is that the matrix on the right-hand side in this formula can be expressed in terms of genus 2 Eisenstein series. And there are some, as I said, there are some explicit formulas for such functions. Unfortunately, our formula doesn't show the explicit dependence on specific e's at genus 2. This is some subject for further research, how to get actually explicit formulas, not in terms of Giger kernel, which is the sum of Eisenstein series, but in terms of explicit genus 2 Eisenstein series at depending on the period matrix. So that the question that we are going to study later on. But at the moment, this is the farthest generalization of the classical Ramanujan formula. Let me remind you the first formula which we start from this formula. You see the genus 1 formula for the first power of the modular discriminant. You see it's the same. We don't see a theta function, but they could be if we switch to a different representation, and the determinant expressed in terms of classical Eisenstein series. So our last formula is the generalization that we get currently for the genus 2 case. So that genus 2 right-hand side can be substituted with higher genus. The question is why we need this, why it's important. As I said at the very beginning, I don't know why I should not pretend that I know why they do that, but in number theory, they, again, as I said, they express powers of eta functions in terms of powers of tau in some numerical calculations, you see. I don't know, but they definitely, there are some papers expressing they use some numerical methods in order to find this, and we have explicit formula which you just substitute the cube in all the definition of the right hand side, which are not approximations, those are explicit formulas. You can substitute values of q, everything on the right hand side can be expressed as q series. You substitute a specific value of q and you get dependence on tau. The other question is that we can use those formulas. Those formulas come from computations of higher genus correlation functions, and in certain cases, such formulas can be used back to in order to get some explicit expressions for correlation function. And finally, when we consider not just partition functions, but endpoint functions, more complicated cases of this expression, when we have also here vertex operators, there are formulas for such functions. We can define a cohomology related to those functions, or can define a cohomology which is related to the vertex operator algebra itself. And formulas, as we saw at the beginning, as much as other formulas relating classical Eisenstein series can be used in order to compute explicitly cohomology for object related to vertex algebras. So these are three reasons why we need these formulas. So it's quite applied nature. Those formulas are of quite applied nature. Since we have exact expressions, we don't need to estimate anything. We just substitute parameters. Yes, machine learning. Okay, so that's probably all material that I want to present here.
Oh, yeah. I hope that it can be applied nowadays, data analysis.
Yes. Coding. It's actually also related to some coding. Cryptography, yeah.
Is there some more questions? Doron Skoda, you know him, yeah?
Yes, yes, of course.
So,
I don't see him.
yeah. See, thank you.
Okay.
If there are no more questions, let us thank the speaker again.